By the end of this video, you should be able to look at a spectrum like this and figure out the structure of the organic molecule that caused it. Let's start with the fundamentals. What is NMR? NMR stands for nuclear magnetic resonance. You might have heard of a similar technique in medicine called magnetic resonance imaging, or MRI. In fact, when MRI was first developed, it was originally called NMRI, or nuclear magnetic resonance imaging. But the nuclear part was dropped because this was during the Cold War when people weren't too keen on the sound of anything nuclear. As chemists, we know that the word nuclear simply refers to the atomic nucleus, and as such, there isn't anything inherently dangerous about it. As the names suggest, both MRI and NMR involve the use of magnets. With MRI, we get an image, and with NMR, we get a spectrum. So, how does NMR work? Let's imagine we have a very big, very strong magnet. Inside this magnetic field, we put a much smaller bar magnet. The bar magnet will rotate so that it's parallel with the external magnetic field because this is its lowest energy state. Now, if we reach in and physically exert our own energy, we can rotate the bar magnet into an anti-parallel position. We can think of the anti-parallel position as a high energy state. With a stronger external magnetic field, we would need to exert more energy to rotate the bar magnet, and hence there will be a bigger difference in energy between the parallel and anti-parallel states. Remember this because it's going to come up again later. If we were now to release the bar magnet, it would rotate and relax back to its low energy position parallel with the external magnetic field. So, in summary, by adding a certain amount of energy to the system, which depends on the strength of the external field, we can rotate the magnet to a higher energy state, which will then relax back to the low energy state after a brief period of time. This is essentially how NMR works, because certain atomic nuclei can behave as tiny magnets. When we put these nuclei into a large magnet, they will line up with a magnetic field. Next, we add energy to the system by pulsing them with radio waves. The nuclei will absorb certain radio photons and will be moved into an anti-parallel position. This is called resonance. After a short period of time, they will realign themselves with the field and release the absorbed photons, which are then detected to give a peak in the spectrum. Now, not all atomic nuclei will interact with a magnetic field. The only nuclei that can are the ones which either have an odd number of protons or an odd number of neutrons. This is because protons and neutrons have certain intrinsic properties such as mass and charge, but they have another one called spin. With an odd number of protons or neutrons, the nucleus will have an overall spin which allows it to behave as a magnet. The two most important isotopes in organic chemistry that can be examined by NMR are carbon-13 and hydrogen-1. Hydrogen-1 NMR is more commonly known as Proton NMR, since a hydrogen-1 nucleus only consists of a single proton. Carbon-12 has even numbers of protons and neutrons, so it's not visible by NMR. However, even though carbon-13 only makes up around 1.1% of all carbon, it's important to bear in mind that any sample of any organic compound that you might be examining by NMR will contain trillions and trillions of molecules. So, statistically, throughout the whole sample, there will be enough carbon-13 in each position of the molecule to allow you to see the entire structure. Whatever our sample is, when we run it in an NMR spectrometer, we'll need to dissolve a small amount of it in an appropriate solvent. For NMR, we use a solvent such as CdCl3, also known as deuterated chloroform. Regular chloroform has the molecular formula CHCl3. Since this contains a hydrogen of its own, it would leave a significant peak on a proton NMR spectrum, which could obscure peaks from your sample. To avoid this, we use solvents which do not contain any hydrogens. Deuterated chloroform has had its regular hydrogen swapped out for a deuterium atom. Deuterium is an isotope of hydrogen which has both a proton and a neutron in the nucleus, giving it a mass number of 2. Deuterium resonates at a different frequency to regular hydrogen, so deuterium peaks don't show up when doing regular proton NMR. This means there's no risk of a deuterated solvent obscuring any hydrogen peaks. The same solvent can be used for carbon-13 NMR, even though it contains a carbon atom, because it will produce a very recognizable peak which can be removed before we need to do any analyzing. So, the next question is, how do we distinguish between different nuclei with NMR? Well, that depends on the environment of the nucleus. The environment is determined by what that atom is bonded to. We need to be able to look for equivalent environments. Let's take a look at propane. This molecule has 3 different carbon atoms. Let's look at what each one is bonded to. Carbon number 1 is bonded to 3 hydrogens and 1 ethyl group. Carbon number 2 is bonded to 2 hydrogens and 2 methyl groups. Carbon number 3 is bonded to 3 hydrogens and 1 ethyl group. So, carbons 1 and 3 are bonded to the exact same groups and are therefore in identical environments to each other. This means that propane only has 2 carbon environments. It also has 2 hydrogen environments, as all hydrogens bonded to the same carbon are identical to each other. So, all 3 hydrogens coming from carbon number 1 are all in the same environment, making them identical to the hydrogens coming from carbon number 3. Let's take a look at a more complicated example with 2-methyl-propyl ethanoate, also known as isobutyl acetate. We'll number the carbons again to make it easier to navigate the molecule. Pause the video here and see if you can identify the number of carbon and hydrogen environments. Let's start with carbon. The correct answer is that there are 5 carbon environments. The reason is that carbons 1 and 3 are equivalent. They're both identical methyl groups coming from carbon number 2. They're bonded to the exact same groups and hence are in the same environment. All of the other environments are unique as they are each bonded to different groups. How about hydrogen? There are 4 hydrogen environments in this molecule. Again, the hydrogens on carbons 1 and 3 are all equivalent, so they're all in identical environments. Carbon number 5 has no hydrogens on it, and all of the other hydrogen environments are unique, as their respective carbons are all bonded to different groups. So, that's how to identify the environment. But why does the environment affect the position of the NMR peak at all? Aren't the nuclei the same either way? Well, yes and no. Every carbon-13 nucleus is identical in that they all consist of 6 protons and 7 neutrons. However, when they're in different environments, the electron cloud surrounding the nuclei changes. Just like protons and neutrons, electrons also possess a spin, so they can help to shield the nucleus from the external magnetic field. If a carbon-13 is bonded to an electronegative element like oxygen, the electrons around the carbon-13 nucleus are pulled away. When the electrons are pulled away, the nucleus is more exposed, which allows it to feel the external magnetic field even more strongly than it normally would. Remember earlier when I said that with a stronger external magnetic field, we would need to exert more energy to rotate the bar magnet, and hence there will be a bigger difference in energy between the parallel and anti-parallel states? Well, since our carbon-13 nucleus is now feeling a stronger external magnetic field due to the de-shielding, it will also have a bigger difference in energy between the parallel and anti-parallel states. This means that more energy is required to flip it, so it absorbs a higher frequency radio photon when it flips, and later emits that higher frequency radio photon when it flips back. So, in summary, when a nucleus is in a different environment, its electron cloud is affected, meaning it will have a different amount of shielding compared to other environments, which changes how strongly it feels the external magnetic field, which in turn changes how much energy is required to flip it. More de-shielded nuclei require more energy to flip than more shielded nuclei. This results in different environments producing peaks in different positions on the spectrum. An NMR spectrum looks something like this. Notice that with NMR spectra, the horizontal axis is backwards, with 0 on the right-hand side and the numbers getting bigger towards the left. The chemical shift is related to the radio frequency and is measured in parts per million. If a nucleus is more de-shielded, its peak will have a higher value of chemical shift and is described as being downfield. If a nucleus is more shielded, its peak will have a lower value of chemical shift and is described as being upfield. So, The closer a nucleus is to an electronegative atom, the more de-shielded it will be. As a result, it feels the external magnetic field more strongly, so more energy is required to flip it. This translates to a higher chemical shift, so the peak will appear further to the left or more downfield. When running an NMR spectrum, we need to add a small amount of a reference standard to our sample. The reference standard we use is tetramethylsilane. The reason we use this is that it has 4 carbons all in the same environment and 12 hydrogens all in the same environment. This means it will give a very clear peak whether it's used for carbon-13 NMR or for proton NMR. The other reason is that carbon is actually more electronegative than silicon, so the carbons, and by extension the hydrogens, are actually partially negative in this molecule. In other words, they're quite strongly shielded, especially compared to the carbons and hydrogens in most organic compounds. As a result, the carbon nuclei and the hydrogen nuclei in this molecule feel the external field less than most other carbons and hydrogens, so a relatively small amount of energy is required to flip them. This gives rise to a peak which is more upfield than the peaks in our actual sample. We set this peak as 0 ppm, and the other peaks are all relative to it. The TMS peak is then removed, so it usually doesn't appear in the spectrum. We could go into a lot more depth with NMR and talk about concepts like quantum numbers, precession, and Fourier transforms, but what we've covered so far should hopefully give you a decent enough fundamental understanding about how the technique works. Now, let's start analyzing some spectra. This is the carbon-13 NMR spectrum for a molecule with the molecular formula C3H8O. In this spectrum, we can see that there are 3 peaks, which tells us that each of the 3 carbons in the molecule are in 3 unique environments. By looking at the positions of the peaks and comparing them to values from the datasheet that will be given in an exam, we can see that these 2 peaks are in the range we'd expect for carbons bonded to other carbons, and this peak is in the range for a carbon bonded to an oxygen. By the way, be aware that the exact values on the datasheet can vary slightly from exam board to exam board since they're more like guidelines. Peaks can exist outside of these ranges depending on what else is bonded nearby. Piecing all of this information together, this makes it likely that this molecule is propan 1-ol. This fits with the molecular formula as well as the number of environments and the positions of the peaks. It couldn't be the structural isomer propan 2-ol because this only has 2 carbon environments, not 3. In an exam, you're unlikely to be asked to solve a complicated structure using carbon-13 NMR because it's very difficult to piece together a larger molecule using this technique only. For more complicated structures, you would instead use Proton NMR. The reason we use Proton NMR instead of carbon-13 NMR is that there are 2 additional pieces of information we can learn to help us solve the structure. Let's take a look at the Proton NMR spectrum for a molecule with the molecular formula C6H12O2. Just like with the carbon-13 NMR spectrum, we can look at the number of peaks to determine the number of proton environments. In this case, there are 4. And we can look at the positions of the peaks to determine what kind of environments there are. However, we have even more information that can help us here. The first piece of extra information is the peak intensity, also known as the peak area or the peak integration. These numbers next to the peaks represent the ratio between the numbers of protons in each environment. So, going from left to right, we have a ratio of 2 to 3 to 1 to 6. Now, it's important to bear in mind that this is just the ratio between the numbers of protons in each environment. So the actual numbers of protons could in theory be 4 to 6 to 2 to 12, or even 20 to 30 to 10 to 60, although this one's pretty unlikely. However, since we know that our molecular formula contains 12 hydrogens, this ratio must represent the actual number of protons in the structure, as 2 plus 3 plus 1 plus 6 equals 12, so all the protons are accounted for. So these numbers tell us how many hydrogens can be found in each environment. The second bit of extra information is the peak splitting. You'll have noticed that a couple of these peaks look a bit weird. This is because they've been split. Splitting is caused by the protons in adjacent environments. The amount of splitting tells us how many protons are next door to the protons in that environment, and is due to something called the N+1 rule. Here, N represents the number of adjacent protons. Let's say we're looking at environment A, and there are 2 protons next door in environment B. Due to the N+1 rule, the peak for environment A will be split into 2 plus 1, which is 3 peaks, known as a triplet. Let's go through the different splitting possibilities. If the peak is not split and remains as a single peak, it's called a singlet. The N+1 rule tells us that there would be 0 adjacent protons. If the peak is split into 2, it's called a doublet, and the N+1 rule tells us that there would be 1 adjacent proton. If the peak is split into 3, it's called a triplet and will have 2 adjacent protons. If it's split into 4, it's called a quartet and will have 3 adjacent protons. Any more than that, we can call it a multiplet. Let's go back to our spectrum and go through what we've got so far. We have a peak at around 0.9 ppm, which is a doublet with a peak intensity of 6. This tells us that there are 6 protons in this environment with 1 proton on the carbon next door. The next peak is around 1.8 ppm and is a multiplet with a peak intensity of 1. This tells us that there is 1 proton in this environment with many hydrogens on the adjacent carbons. After this, we've got a peak at around 2 ppm, which is a singlet with a peak intensity of 3. This tells us that there are 3 protons in this environment with no adjacent hydrogens at all. Finally, we have a peak at around 4.3 ppm, which is another doublet, but this one has a peak intensity of 2. This tells us that there are 2 protons in this environment and that there is 1 proton on the carbon next door. In an exam, you should write all of this out because you can pick up a lot of marks here even if you can't figure out the final structure. Now comes the tricky bit, piecing it all together. This can take a lot of practice, so just stick with it and it should get easier. The first thing that stands out to me here is that we have 2 environments which each have a single proton next door, as evidenced by the fact that they're both doublets. In addition to this, we have another environment which contains a single proton, as evidenced by the fact that it has a peak intensity of 1. Moreover, the peak for this environment is a multiplet, indicating that it's adjacent to many other hydrogens. All of this points to the fact that these 2 environments are adjacent to this environment. These 2 have 1 proton next door. This environment contains 1 proton. They fit together. So, this single proton is most likely a CH and must have 6 protons on one side and 2 protons on the other side. This means we'll have 2 methyl groups on one side and a CH2 on the other side. So far, this fits with the peak intensities and with the peak splitting. So, if we're correct so far, we've already accounted for 4 out of our 6 carbons and 9 out of our 12 hydrogens. We still have to find where our 2 remaining carbons, 3 remaining hydrogens, and 2 remaining oxygens fit in. The one peak we haven't accounted for yet is the singlet with a peak intensity of 3. This will most likely be a CH3 group, and since it's a singlet, it cannot have any adjacent hydrogens. This tells me that it can't be next to the CH2 group here. It must be separated somehow. If we have a CH3 group somewhere at the other end of the molecule, we now have 1 remaining carbon and 2 remaining oxygens to fit in. The most likely place to fit them will be an ester group. This would separate the CH3 from the rest of the hydrogens, leaving its peak as a singlet. The only question remaining is, which way round does the ester group go? We can figure this out by the peak positions. If we look at the datasheet, we can see that a proton which is bonded to a carbon which is bonded to a carbonyl group can usually be found in the region 2 to 3 ppm. A proton which is bonded to a carbon which is single bonded to an oxygen can usually be found in the region 3 to 4.1 ppm. So, since the CH3 peak is around 2 ppm, it must be bonded to a carbonyl, so the ester linkage will be this way round. This gives us 2-methyl-propyl ethanoate, also known as isobutyl acetate, the same molecule we looked at earlier when learning about environments. Again, don't worry if this all seems overwhelming to you. It will take practice to be able to do this for yourself, but hopefully you're following the logic behind everything so far. Let's take a look at another Proton NMR spectrum, this time for a molecule with the molecular formula C6H10O2. Pause the video here and see if you can solve this structure before I go through it. Okay, so I'm going to first go through the peaks present. There are 4 peaks in total, so there are 4 proton environments in our molecule. We have a peak at around 1 ppm, which is a triplet with a peak intensity of 3. This tells us that there are 3 protons in this environment, with 2 protons next door. Next, we have a peak at around 2.2 ppm, which is a singlet with a peak intensity of 3. This tells us that there are 3 protons in this environment with no adjacent protons. We then have a peak at around 2.5 ppm, which is a quartet with a peak intensity of 2. This tells us that there are 2 protons in this environment with 3 protons next door. Finally, we have a peak at around 3.6 ppm, which is a singlet with a peak intensity of 2. This tells us that there are 2 protons in this environment with no adjacent protons. Now, the first thing I notice here is a pair of peaks that I always look out for in Proton NMR spectra. We have a triplet with a peak intensity of 3 and a quartet with a peak intensity of 2. The triplet with a peak intensity of 3 must be a CH3 group, and since it's a triplet, there are 2 protons next door. The quartet with a peak intensity of 2 must be a CH2 group, and since it's a quartet, there are 3 protons next door. So, these 2 peaks are connected. It's just a CH2-CH3 group. You'll often see these peaks in an NMR spectrum because they represent the end of an alkyl chain. So, just like that, we've already assigned 2 of our 4 peaks. The other 2 peaks are both singlets, which tells me that both of these environments are isolated, as in, they're not adjacent to any other hydrogens. One of them will be a CH2 group since it has a peak intensity of 2, and the other will be a CH3 group since it has a peak intensity of 3. Now, how can we ensure these groups are all separated so that the splitting all makes sense? Well, that's where the oxygens come in. So far, we've assigned 4 out of 6 carbons, all 10 hydrogens, but neither of our oxygens. There are still 2 carbons and 2 oxygens to fit into the structure. This tells me that there are most likely a couple of carbonyl groups separating the other groups from each other. Piecing this all together, we get hexane 2,4-dione. This also explains why the peak for this CH2 group is shifted so far downfield, outside the normal range for a proton which is bonded to a carbon which is bonded to a carbonyl. It's because it's bonded to not 1, but 2 carbonyl groups. This is a great example of how the ranges given in a datasheet are more like guidelines rather than strict boundaries. Let me know in the comments how close you got to solving this structure. Something else I'd like to briefly talk about is OH peaks and NH2 peaks. Both of these will always show up as a singlet when looking at them in Proton NMR. The other thing is that if we look at the datasheet, these peaks can show up anywhere. So, we have a way to confirm whether or not a given singlet is due to an OH or an NH2. What we need to do is rerun the sample through the NMR spectrometer with a little bit of D2O mixed in. D2O is deuterated water, also known as heavy water. It's the same as regular water, but where each hydrogen has been replaced by a deuterium atom. Remember, deuterium is an isotope of hydrogen, but with a neutron in the nucleus as well as a proton, giving it a mass number of 2. When we add D2O to our sample, the hydrogens in any OH or NH2 groups in the molecule are exchanged for deuterium atoms. Remember, since deuterium resonates at a different frequency to regular hydrogen, the peaks don't show up when doing regular Proton NMR. This means that any OH peaks or NH2 peaks that were present in the original spectrum will disappear in the second spectrum when we add D2O. Okay, now that we've gone through a few examples together, hopefully this is all starting to make a bit more sense. Again, don't worry if you're still finding it difficult. It will take practice to be able to do this. There's also nothing wrong with a bit of trial and error when doing this for yourself. When you get close, try and draw out a possible structure and see if it works with all the information you've got. If not, you can keep trying until you get there. If you found this video helpful, please consider subscribing to support the channel and let me know in the comments if you have any questions.